Welcome to the NORA online Bioheat Technical Understanding and Guidance session. What is Bioheat? Bioheat is a blend of number 2 petroleum heating oil and biodiesel, both of which meet the appropriate ASTM specification. ASTM D396 describes fuel with up to 5% biodiesel as equivalent to heating oil. ASTM D396 also has specification for blends from 6 to 20% biodiesel, otherwise known as B6 to B20. Now, since B5 Bioheat is considered to be the same as number 2 oil, many consumers are not aware that they are already using this lower carbon, environmentally friendly fuel. Some people may question, why move to Bioheat? First, the biodiesel in Bioheat is produced from a variety of renewable resources, such as plant oils, animal fats, recycled grease, and even algae, making it one of the most sustainable fuels on the planet. And with biodiesel, there's no sacrificing food for fuel. Oils and fats for biodiesel are a minor byproduct of producing high-protein feeds and quality meats. Second, it's made in the USA and can reduce our dependence on foreign oil. Third, the U.S. government considers biodiesel to be an almost carbon-neutral fuel because the plants that are the sources of the feedstocks for making biodiesel absorb carbon dioxide as they grow. The absorption of carbon dioxide by these plants offsets the carbon dioxide that forms while making and burning biodiesel. And fourth, biodiesel is the best option for oil heat to meet carbon reduction goals. Additionally, individual states are setting greenhouse gas reduction targets that just can't be met by using standard number 2 petroleum oil. Here's a sample of a few. New York's mandate is for a 50% reduction in greenhouse gases by 2030 and a 100% reduction by 2050. Connecticut wants an 80% reduction by 2050. Pennsylvania wants a 33% reduction by 2030, and Massachusetts wants an 80% reduction by 2050. Let's take a look at some of the differences between standard number 2 heating oil and Bioheat. There are different ASTM standards for number 2 oil and B100. B100 has fewer BTUs per gallon than number 2 oil, and a B20 blend contains approximately 1.8% less BTUs than number 2 oil. The flash point of a fuel is the maximum temperature at which the fuel can be safely stored and handled without a serious fire hazard. The flash point of number 2 oil ranges from 100 degrees to 180 degrees Fahrenheit, whereas the flash point of B100 ranges from 200 degrees to 338 degrees Fahrenheit. Cloud point is the temperature at which wax crystals begin to form in the fuel. These crystals can restrict fuel flow by clogging filters and strainers. Now, ASTM does not list a cloud point specification for heating oil, but typically the cloud point for number 2 oil is 10 to 15 degrees Fahrenheit. A B20 blend would typically be 15 to 25 degrees Fahrenheit, and the cloud point for B100 ranges from 32 to 63 degrees Fahrenheit. The actual cloud point for biodiesel can vary depending on the feedstock. It is important to note that suppliers will be supplying blends that are appropriate for the markets they sell in. Viscosity is the thickness of a fuel and its resistance to flow. The higher the number, the thicker the fuel, and the higher its resistance to flow. The viscosity of B20 is essentially the same as number 2 oil. Straight number 2 oil contains no oxygen. B100 contains 11% oxygen by weight. What this oxygen means for the consumer and the service technician will be covered in detail later in this presentation. Due to the differences between number 2 oil and Bioheat, NORA and several manufacturers have invested a significant amount of time and money into research to determine whether or not Bioheat can be used with current equipment in the field. Let's take a look at some of these areas of concern and the results of the research that has already been completed. The intent of the research was, and continues to be, the safety and efficiency of oil heat equipment. The industry needs to be sure that oil heat equipment using Bioheat will not cause any health, safety, or performance issues. Those who will be working with Bioheat have several valid concerns that need to be addressed to ensure that they are confident the fuel will perform without adversely affecting their customers, themselves, or their heating system. Among the questions that will be addressed in this course are: what is the shelf life of Bioheat? How long will the fuel remain stable while in storage? Is Bioheat compatible with yellow metals such as copper and brass? Will the components of existing units in the field perform as required? How will pump seals, gaskets, and O-rings hold up to Bioheat? Does the fact that there is oxygen in Bioheat mean that oil burners will have to be adjusted each time a different blend is delivered to a customer's tank? How does Bioheat perform in cold conditions? Will the slightly lower BTU content of biodiesel affect the firing rate or increase fuel use? Will CAD cell primary controls be able to see a biofuel flame? Will customers experience nuisance lockouts because the CAD cell cannot see the flame? Fuel units sometimes stop working because sticky residues clog up the gears. Will Bioheat make this situation worse? And will burners be able to properly atomize a higher viscosity fuel? Will appliances require more frequent maintenance because of poor atomization? Answers to concerns about fuel properties, including shelf life, pour point, viscosity, and BTU values, are presented in the following slides. In regard to the question about shelf life, it is important to understand that all fuels degrade over time. Fuels that are stored for long periods of time and subject to temperature extremes can form sediment and gums that clog filters, strainers, and nozzles. There is no specific shelf life for number 2 fuel, but there is one for biodiesel. B100 has a minimum shelf life of 6 months. And recent data shows that B20 available in the marketplace appears to have a minimum shelf life of 1 year. The shelf life of number 2 varies and can be similar to biodiesel. Additives are available that improve the shelf life of both number 2 oil and biodiesel. The pour point of a fuel is the lowest temperature at which it will flow. Pour points can vary, although there is normally no issue with in-ground tanks. Additives and kerosene are often added to outside above-ground tanks to ensure that fuel can reach the burner on the coldest days of the year. At a B20 level, there doesn't appear to be any issues that require additional actions over those that are required for number 2 oil. Companies using B20 have not experienced issues related to the fuel's viscosity. And as the industry moves to higher blends of biodiesel, the viscosity of the fuels might lead to poor atomization. Simply raising the pump pressure alleviates any issues related to the viscosity of Bioheat. The BTU content of B100 averages 8% less than that of number 2 oil. B20 averages approximately 1 to 2% less than number 2 oil. This is similar to the BTU reduction that occurred when the industry switched to ultra-low sulfur heating oil, commonly referred to as ULSD. The switch to ULSD resulted in less fouling of heat exchangers and less degradation of heating system efficiency during the year, more than compensating for the slight difference in BTU content. Bioheat has even less sulfur than ULSD and burns cleaner than number 2 oil. We expect its use to have similar effects to what has been experienced with ULSD. The slight difference in BTU content will have little or no effect. Now let's move on to material compatibility. The questions that have been raised about the material compatibility of Bioheat are primarily regarding fuel degradation from yellow metals like copper and brass and possible leaks from pump seals, gaskets, and O-rings. Laboratory tests have shown that B20 does not cause leaks or excessive swelling of components in standard fuel units. The lack of fuel unit issues with Bioheat is confirmed by the thousands of burners in the field that have been using B20 and higher for over 12 years with no problems. To further address the questions about the ability of current fuel pumps to tolerate increasing blends of biodiesel, NORA conducted a series of laboratory tests running B5, B20, B50, and B100 through a bank of Suntech A2VA-7116 model pumps. These are very common in the field and are rated for up to B5. These were not modified in any way for the test. The pumps were cycled at intervals of 5 seconds on and 5 seconds off. One full cycle consisted of one on and one off period, or about 10 seconds. Each pump was cycled 500,000 times. Conservative estimates show that 10,000 cycles are performed by an average pump in a home annually. This test simulated 50 years of operation in the field for each pump. Scheduled removal inspection and testing was performed at 100,000, 200,000, and 350,000 cycle breakpoints. Let's look at some sample piston faces that went through the testing at B5 for the full 500,000 cycles. Although some wear and tear is evident, there is no indication of failure. Now let's look at samples of piston faces that went through the testing with B100. Again, there is some wear and tear evident, but the results are similar to those that ran with B5. The data and inspections showed that increasing the blends of biodiesel did not have any effect on the cutoff times for any of the pumps tested. Some pumps did show some wear and tear on elastomers, piston faces, and diaphragm seats. However, this is consistent with the normal wear and tear found with pumps running B0. The wear with B100 was consistent with B0. No additional wear was found. It is important to note that there are some system components that require specific bio-approved materials. For example, manufacturers now have filters and flexible lines and deaerators that are rated up to B100. NORA recommends that these components be upgraded as needed. To address the questions about yellow metals, long-term stability tests were performed. These tests involve multiple samples of number 2 oil and B20 that were heated in an oven at 110 degrees Fahrenheit for 9 weeks to simulate being in the field for 9 months. Half of the samples were exposed to copper for 24 hours before the test. After 9 weeks, the samples were removed and the amount of filterable and adherent particles were measured. Filterable particles are those that can be trapped by the fuel filter, and adherent particles are those sticky residues that sometimes are found in fuel units that have become bound. The filters on the top row were used with fuels not exposed to copper. The filters on the bottom were used with fuels exposed to copper. The 4 filters on the left are the number 2 oil filters, and the 4 on the right are the B20 filters. And as you can see, there are very few particulates trapped on the filters for the number 2 oil and the B20 that were not exposed to copper. However, the filters for both fuels that were exposed to copper show a significant amount of particulates. The filters for the number 2 fuel appear to have trapped much more particulate than the ones that filtered the B20. These results show that the B20 did not have a worse reaction to copper than the number 2 oil. However, these tests do provide additional evidence to support the industry's efforts to reduce our fuel's exposure to copper and to convert 2-pipe systems to 1-pipe systems whenever possible. These pictures show the adherent particulates from the fuels that were exposed and not exposed to copper. The pictures on the left are the bottles that contain B20. There does not appear to be a significant presence of adherent particulates. The bottles on the right are the bottles that contain number 2 oil. As you can see, there is significant buildup of adherent particulates when the fuel was exposed to copper. These results show that B20 does not contain more adherent particulates than number 2 oil. The NORA lab has received and analyzed a significant number of bound fuel units. Some have come from systems that did not use any bioheat, and others from systems using bioheat. The industry has been aware of the detrimental effects of copper for many years. The situation will not get any worse using bioheat. Now we'll address the questions involving combustion air settings, CAD cell readings, smoke, and carbon monoxide. The industry needs to be sure that we can safely change from high blends of biodiesel to lower blends without causing issues with the appliance or creating dangerous levels of carbon monoxide. If any of these situations could occur, Changing from high blends to lower ones would require that a service technician adjust the burner immediately after each delivery. We also have the same concerns about switching from low blends to high blends. To address these questions, extensive testing was performed at NORA's research lab. All testing involved properly adjusting burners with a combustion analyzer for a certain biodiesel blend and then switching to a different blend without making any adjustments. Running the unit at a steady state for 5 minutes and then recording the results. Throughout the testing, carbon monoxide readings were under 10 parts per million and were considered to be near zero. The first set of tests were performed on a Carlin EZ1 burner. The burner was adjusted for and operated with B100. The smoke reading was 0 and the CO2 was measured at 11.3%. Carbon monoxide in the flue gas was measured as near zero. The fuel was then switched to number 2 oil, or B0. The smoke reading remained at 0 and the CO2 went up to 11.7%. Carbon monoxide remained at near zero. The next step in the Carlin EZ1 testing started with adjusting the burner using B20, then switching to B0, and then switching again to B100. Combustion testing showed that the carbon dioxide reading went up 0.1% when the change was made from B20 to B0, and it went down 0.3% when the change was then made to B100. Smoke remained at 0, and carbon monoxide remained at near 0 throughout the test. The next set of tests were performed on the Beckett AFG burner using the same parameters as those used in the testing of the Carlin EZ1. Once again, the burner was adjusted using a combustion analyzer for a certain biodiesel blend and switched to different blends without making any adjustments. For each blend, the burner was operated at a steady state for 5 minutes, and the test results were recorded. To determine if decreasing blends might be problematic, the burner was adjusted for B100, then the fuel switched to B50 and switched again to B0. The CO2 difference between the three fuels was 0.2%. Once again, the smoke remained at 0 and the carbon monoxide remained at near 0 for all three fuels. To determine if increasing blends might be problematic, the burner was adjusted for B0 and then the fuel was switched to B50 and switched again to B100. The CO2 difference between the three fuels was 0.2%. Smoke readings remained at 0 and the carbon monoxide remained at near 0 for all three fuels. The preliminary results gained from testing with the Carlin EZ1 and the Beckett AFG are that as long as the burner is properly tuned to begin with, there are no carbon monoxide or smoke issues involved with increasing or decreasing biodiesel blends, and that the CO2 differences are minimal. The next step in this first round of testing was to determine if CAD cell resistance readings were so much higher with biodiesel blends that burners would shut down on safety, causing nuisance lockouts even when the burner was operating properly. The Beckett Genesis display tool was used to measure CAD cell resistance for both burners in this test. The tests were carried out in a manner similar to the testing on combustion. The burners were adjusted using testing equipment and run at steady state for 5 minutes before the readings were recorded. The fuels were then switched, no burner adjustments were made, and the process was repeated. Carbon monoxide levels of 10 ppm or less were considered to be near zero. For the Carlin EZ1 burner, the CAD cell reading was B0 at 260 ohms. The reading went up to 620 ohms when the fuel was switched to B100. Next, the Beckett AFG burner was adjusted for B0 and then switched from B50 then to B100. And the readings were 260 ohms at B0, 340 ohms at B50, and 740 ohms at B100. While the readings more than doubled when the level of biodiesel was increased from B0 to B100, it was significantly less than the level that would cause the burner to shut off on safety. The Honeywell R8184 control lists 1600 ohms as the lockout threshold. The B100 readings of the Carlin EZ1 and the Beckett AFG are less than half of that. The Beckett Genesis control locks out at 4,000 plus ohms. And the Carlin Pro X lockout threshold can be selected to either 3,300 or 5,300 ohms. Clearly, using a higher level of biodiesel should not cause properly operating burners of these two types to experience nuisance lockouts. The first round of testing demonstrated that there should be no combustion or flame sensing concerns about the burners that were tested. However, there are many other oil burners in the field, and NORA decided that more testing was needed before an industry-wide move to higher blends is advisable. These tests included the Beckett NX burner, the Riello F3, and an obsolete 1725 RPM non-flame retention Mohawk burner. The fuels tested for each were B0, B20, B50, and B100. Each burner was first adjusted for B0, then blends were increased to B20, B50, and B100 with no burner adjustments. Then each burner was adjusted for B100, and the blends were decreased to B50, B20, and B0 with no burner adjustments. The parameters that were measured include carbon dioxide, carbon monoxide, CAD cell readings, and flue gas temperature. Combustion efficiency calculations for biodiesel blends are not currently programmed into most combustion analyzers. The readings shown were calculated by NORA's Research Lab Director, Dr. Tom Butcher. It is important to note that many of the differences reported are within fractions of a percent of carbon dioxide or single digits of carbon monoxide. These variations are within the combustion testing equipment's margin of error. Here are the results with the Beckett NX when the biodiesel blend was increased from B0 to B100. The carbon dioxide readings decreased 0.1%, and this is within the margin of error. The carbon monoxide decreased 1.1 part per million. The CAD cell readings increased by 736 ohms. The flue gas temperature decreased by 5 degrees, and the combustion efficiency decreased by approximately 0.2%. Here are the results for the Beckett NX when decreasing blends of biodiesel were used, and smoke remained at 0 for all fuels once again. The CO2 reading stayed the same at 12.1%. For the carbon monoxide, there was an increase of 0.1 part per million. CAD cell readings decreased by 540 ohms. Flue gas temperatures decreased by 9 degrees. And the combustion efficiency increased by approximately 0.5%. Testing the Riello F3 and increasing the biodiesel levels from B0 to B100 gave the following results. And again, smoke remained at 0 for all fuels. The CO2 reading. There was a decrease of 0.2% from B0 to B50. And for carbon monoxide, there was a decrease of 0.2 parts per million. CAD cell readings increased by 25 ohms. Because of the difference in design of the flame sensing components of Riello burners, CAD cell readings were measured by installing a standard CAD cell assembly into the burner's air tube. Flue gas temperatures decreased by 1 degree, and combustion efficiency decreased by approximately 0.2%, again for B50. Increasing to blends higher than B50 were problematic. NORA is currently having discussions with Riello to resolve the situation. The results when decreasing biodiesel blends with the Riello F3 were as follows, and smoke remained at 0 for all fuels. The carbon dioxide reading increased by 0.9% when decreasing from B100 to B0. Carbon monoxide stayed the same. CAD cell readings decreased by 1,374 ohms. The flue gas temperatures decreased by 4 degrees, and combustion efficiency increased by approximately 0.8%. Here are the results with the increasing blend levels with the Mohawk burner, and remember, smoke remained at number 1 for all fuels. The carbon dioxide readings, well, there was an increase of 0.1% from B0 to B100. Carbon monoxide had a decrease of 5 parts per million. CAD cell readings increased by 407 ohms. Since CAD cell technology was not available when the Mohawk burners were manufactured, CAD cell readings were measured by installing a standard CAD cell assembly onto the burner firing assembly. The flue gas temperature decreased by 2 degrees, and combustion efficiency decreased by approximately 0.4%. Now let's take a look at what happens when the decreasing blends of biodiesel were used in the Mohawk burner. And once again, smoke remained at a 1 across all the fuels. The CO2 reading increased by 0.1%. The carbon monoxide had a decrease of 4 parts per million. The CAD cell reading decreased by 1,628 ohms. The flue gas temperature increased by 6 degrees, and the combustion efficiency stayed the same. Testing the additional burners reinforced the observations from the initial testings in the lab, and backed up by tens of thousands of oil heat systems operating on B20 for 12 years or more. There is no efficiency, carbon monoxide, smoke, or nuisance lockout issues involved with increasing or decreasing biodiesel blends to B20. The next area of testing involved fuel units. There have been reports from the field that biodiesel blends are believed to have caused sticky substances to bind up the fuel units and keep them from operating. NORA has received a number of these fuel units for testing and found that they do contain sticky substances, called polymers, that are basically degraded hydrocarbons. Degraded hydrocarbons, commonly referred to as sludge, are not new to the industry. The pictures you see here are from years ago, long before any of us ever heard of biodiesel. They show sludge buildup on fuel filters and nozzles. This sludge issue has been in our industry for years and will continue to be an issue unless we properly maintain customers' fuel tanks. Many of the fuel units that NORA has tested were operated on straight number 2 oil with no biodiesel blends in it. Some others had been operated at B5 or B20. There was no correlation between the use of biodiesel blends and the pumps becoming bound. Nearly all of these fuel units had a varnish on their face and signs of water being present in the fuel. These two fuel units were both bound. The one on the left had been operating number 2 oil with no biodiesel content, and the one on the right had been operating B20. When fuel units do become bound, the common element, regardless of the fuel being used, is water. If there's water in the filter or in the fuel unit, there has to be water in the fuel tank. Straight number 2 oil tends to hold some water in suspension. Today's fuels, ultra-low sulfur heating oil and biodiesel blends, tend to shed water. This water ends up at the bottom of the tank where it speeds up corrosion and degrades the fuel. It is extremely important that tank maintenance, including periodically checking for and removing water, be performed on a regular basis. In addition to regularly checking for water in tanks, it's a good practice to consider dual inline filtration. Research indicates that dual filtration can prevent contaminants from reaching the fuel unit and causing it to bind. Let's take a few minutes to sum up what's been covered so far. Here are the questions that have been addressed. Doesn't biodiesel have a 6-month shelf life? No. ASTM requires that biodiesel has a minimum of 6-month shelf life. Number 2 also has a shelf life, similar to that of biodiesel, but there is no ASTM requirement. Both shelf lives can be extended with additives. Are biodiesel blends compatible with yellow metals and the seals, gaskets, and O-rings in oil heat systems? Laboratory tests have shown that B20 does not cause leaking or excessive swelling of fuel unit components. Additional testing is being conducted on higher blends. Will there be issues with combustion on higher blends? There are certainly no issues with B20. Current data with higher blends shows minor concerns that are being investigated. Is the pour point of biodiesel going to cause problems? Pour point does not appear to be an issue for indoor or in-ground tanks. Above-ground tanks located outside may need to be heated, enclosed, or treated with additives. Is the difference in BTU content going to cause customers to consume more fuel? The 1 to 2% difference in the BTU content of B20, which is similar to the difference with ultra-low sulfur heating oil, may be offset by an efficiency gain due to the fact that Bioheat burns cleaner. 1/8 inch of soot can reduce efficiency by 8%. If Bioheat produces 1/64 of an inch less soot, it makes up for the BTU difference. Will the use of biofuel cause nuisance lockouts because CAD cells can't see Bioheat's cleaner flame? All of the testing done to date indicates that current controls will have no problem sensing the flame of burners firing up to B50. Work is in progress to address the one control that had an issue sensing flame at B100 when the burner was adjusted for B0. Will Bioheat blends cause fuel units to bind up? Research indicates that the issue is no worse with Bioheat blends than it is with straight number 2 oil. The issue appears to be related to degraded fuels and water in fuel tanks. Will the increase in viscosity of biofuels affect cold weather performance and put an extra strain on burner motors? The high limit of viscosity is the same for number 2 and B20. Systems with indoor tanks should not have issues. Outside above-ground tanks may need to be chemically treated or have heaters installed. NORA continues to collaborate with industry members to help advance biofuels research. Currently, field testing is taking place with B40, B50, and B70 in Massachusetts and New York. B100 field testing is taking place in Washington State, Vermont, New York, and Connecticut. NORA will continue to support industry efforts to ensure the safety, efficiency, and affordability of Bioheat. The industry is undergoing challenges and changes. Going forward, the oil heat industry is likely to become the liquid fuel industry. To thrive and prosper, everyone in the industry needs to pitch in to assure the collective survival. Service technicians and installers can help by using the proper instruments to adjust burners, to operate at zero smoke, and within the manufacturer's guidelines. Appliance manufacturers typically provide air-fuel ratio guidance in terms of CO2 for B0. It is recommended that the same manufacturer recommend CO2 levels to be used for making adjustments with Bioheat. In the absence of specific manufacturer's recommendations, a good rule of thumb is to adjust the system to operate at zero smoke with 11.5 to 12% CO2 or 4.5 to 5.8% O2 and 25 to 35% excess air. The sample information sheet presented here shows that the manufacturer's guidelines for specific units that the CO2 should be 11%, the smoke should be 0, and the overfire draft should be negative 0.02 inches. In this situation, adjusting the burner to 35% excess air keeps the CO2 at manufacturer's guidelines regardless of the Bioheat blend. Service technicians and installers can help by checking for water during installations, tune-ups, and service calls. Whenever water is found, it should be documented and the customer should be advised to have it removed as soon as possible. Everyone in the oil heat industry should embrace the change that using Bioheat blends entails. Bioheat will enable the industry to meet its carbon reduction goals. And yes, there will be challenges, but oil heat has faced challenges for years, and Bioheat alone is not a magic bullet. Many customers have aged fuel tanks that contain significant amounts of sludge, and switching to Bioheat is not going to miraculously clean those tanks. Going forward, tank management requires attention. NORA is available to help with fuel quality issues. If you experience problems with fuel units, you can send them back to NORA using an online form. You can find that online form at the end of this course under the heading Additional Resources. The oil heat industry's future is as a low-carbon fuels provider. If we don't accept the challenges and changes necessary by today's low-carbon initiatives, we'll go the same way as the coal industry. Working together, we can face the challenges presented by newer fuels, including ultra-low sulfur and bioheat, and assure a bright future for ourselves and our industry.